Hello, calculus fans. Okay, so there's a relationship between continuity and differentiability, and we're going to demonstrate that with a theorem. Remember, continuity has to do with whether or not there's breaks in a curve. Differentiability has to do with how smooth a curve is. Okay, so let's show what this theorem is. So the theorem says that if you have a function that's differentiable at a point, then it has to be continuous at that point. Now it's important to understand that the converse is not true. Being continuous at a point does not imply that it's differentiable there. So I'd like to show a proof of this theorem because it uses our limit laws, and it's actually not that difficult to prove. So let's keep in mind what it means for a function to be continuous. In order to be continuous at a point, it means that if you take a limit of that function at that limit point, then you can just plug in the value of the function at that point. That's what it means to be continuous. You should go back and look at the definition of continuity. Now there's another way of accomplishing this, and we'll see this at the end, is to prove that the limit as x approaches a of f of x minus f of a, that actually equals 0. We'll be able to see this at the end, why this is true. Now we're given that f of x is differentiable at x equals a, so what we know is that this limit exists, and so we can call the value of that limit f prime of a. So let's do a little bit of algebraic manipulation. We can take the expression f of x minus f of a and rewrite it as this product. You can think about going in reverse, and you can cancel those x minus a's. Now this product only is valid when x is not equal to a, but that's okay because we're going to end up taking a limit and we don't really care what happens at x equals a. So let's do that now. Let's take a limit of the f of x minus f of a, and that's equal to a limit as x approaches a of f of x minus f of a all over x minus a times the quantity x minus a. Now that expression is not valid when x is equal to a, but we're taking a limit, so we don't care what happens at x equals a. So let's go. So our limit laws say that we can write this as a product, and the idea is that each one of these limits exists. The first limit exists because it's the definition of the derivative. You should recognize this entire limit here as being the definition of the derivative. The second limit exists simply because of the direct substitution property, that it's a polynomial function, so we can just plug in x equals a. Okay, so we end up getting the limit, so we just end up with 0. So now let's go back and see why we can piece all this together. If I take f of x, I can just rewrite that as f of x minus f of a plus f of a. And our limit laws say we can break this up. We've just proven that this part here comes out to 0. And this is just a number. F of a is just a number. So our end result is that the limit of f of x is equal to f of a. That's the thing that we need to be able to prove that the function is continuous. So that proves what we want, that we know that f of x is continuous at x is equal to a. So that's the end of the proof. Now I would suggest that the proof is a little bit less important actually than knowing the fact that any function that is differentiable must then be continuous. Okay, that's all for now.